Hello and welcome to video 6. This is looking at the scent protocol. So approximate 25 kilobit per second. Why approximate? You'll see as we go through how this system works. What is scent? It stands for Single Edge Nibble Transmission. So there's that word nibble, which equates to nibble as in 4 bits. Scent is a single wire point-to-point unidirectional communication protocol applied to sensors that convert analog signals like fuel pressure into ECU coded data. So a typical would have been a fuel rail pressure sensor or a mass airflow meter where we may have had an analog output from there. We're now digitizing that, encoding if you like, and sending that over a single wire to an ECU. It returns high resolution sensor data in a cost-effective manner. So it opens up a whole new world of additional features because we've now introduced this protocol. So why do we have scent? So modern vehicle design, driven by emission regulations, has forced the requirement for high resolution 12-bit, sometimes 14-bit data for system sensors reporting parameters such as position, airflow, acceleration, pressure, temperature, ratio. Think of any sensor that we've had in the past. We've now got a digitized output from there. Scent sensors enable a reduction in wiring given a single sensor can return multiple parameters. So that's, we're getting something for nothing really. Nothing's changed wiring wise. It's still power, ground and signal. Whereas that signal would have just been purely an analog signal or maybe a frequency PWM. Not anymore. This is, we can get far more bang for your buck basically. Sense sensors contain fewer components, transmit data faster, and it comes as free if you like, is diagnostic capability and all at low cost. Seems to be a theme, doesn't there, that cost influences everything, doesn't it really? Cost, reliability. It is fault tolerant in our harsh environments. Any environments, think of engine bays, probably the worst environment with ignition and injection events, high current being switched at a ultra fast rate. It generates a lot of noise. You'll typically see this on all signals that you measure, but scent can tolerate that quite comfortably. And it is a standard. Vehicle manufacturers love a standard, and this is covered under the SAE J2716 standard. So standardized protocol, documented, and as you said, Andy, it is that you can find this data. If you want to do a deeper dive, if you can dig that paperwork out, there's far more to discover.
Absolutely. We're going to give you an overview of how it works, but if you do want to find out any more, you're going to put some additional notes on the forum and in the video notes. But if you really want to get into this, that's the standard there.
Yeah. Interesting reading the standard is choose any sensor within the scent protocol, and you can learn out how to decode that, how to transfer the data from that sensor into human readable data. It's digital communication as well, so it simplifies ECU design. What do we mean by that? The computer loves that binary output, doesn't it? Ones and zeros. That is the language. So we've got sensors now speaking the direct language desired by the computer. So that again simplifies ECU design, reducing cost as well.
Yeah, so there's no analog to digital converter inside the ECU with these.
Yeah, all done within the sensor. Yeah. So where do we find scent? Well, given the numerous advantages of scent, VM's implemented this protocol from 2004 and it remains in use today. There doesn't seem to be any demise in scent, if anything the opposite.
Yeah, it's definitely increasing.
Yeah, yeah. Where a traditional analog sensor has been utilised, so mass airflow or DPF pressure, it can be replaced with a scent sensor. So one to be aware of when you're measuring these sensors, checking for the output from the sensor. Don't expect to see just a fixed voltage that changes in relation to perhaps flow or pressure. You're going to see digital data. Below are just a few examples of manufacturers who are using scent, and there they all are. and that is not exhaustive. I think, yeah, that everybody, I shouldn't say that, should I? Because I haven't qualified that, but I've seen it on several vehicles beyond these manufacturers
it's
here.
being increasingly utilised.
Yeah.
Basically, one of the big advantages with Scent is if you've got a sensor that's providing more than one piece of data. So if you look at MAF there, that's useful, but if you could have temperature and MAF on the same sensor, that would be even better. And that's commonly where we're starting to see sensors being used.
Yeah.
And from a technician's point of view, they don't look any different.
Good point.
You don't know until you take the measurement whether what type of sensor that is, unless you've done some just-in-time learning to find out about that particular sensor or ECU.
In fact, that's likely when you're perhaps going to refer to a video like this, or maybe the guided testing Pico, is when you take that measurement for the first time and it's not what you were expecting. All of a sudden we're introduced to scent. So how does it communicate? Well, the transmission is purely from the sensor. There is no two-way communication here. It transmits to the ECU purely receives. The bus voltage will commence switching from 5 volts to 0 volts during signalling. So when the communication is ongoing, you will see 5 volt, 0 volt. It will be arranged in what we call packets. So kind of a little giveaway there that it's not PWM, but again, depending on your time base with PicoScope, you could trip yourself over. Voltage switching or signalling is actioned by the sensor. As I said, the ECU only receives and decodes this data stream. It does not respond. The measured time interval between falling edges of the 5 volt, 0 volt signal represents the data being transmitted, i.e. the bit value. We talked, I think in video 1, about the amount of time a pulse is at a high level or the amount of time it is at a low level will determine how many groups of bits are indicated within that pulse. So 1 bit, a very short pulse, 5 bits, a longer pulse, 5 times 1 pulse. Each scent packet includes a calibration pulse, which denotes the fundamental unit of time, tick time, upon which to determine the bit value or the nibble value. So here's that term, nibble. Now, and you've mentioned this calibration pulse. This is critical to trying to decode this network.
Yeah, so unless you know exactly, because you've looked into the protocol and you know exactly what's on it, to decode scent using the PicoScope, you must know the nibble value.
Yeah, we'll do that. We'll run through the process. So the decoder's pretty good. It'll estimate, and most of the time we'll get it right, but you can qualify that your decoder settings are correct. Typical calibration pulse is 168 microseconds. Again, that sounds like an ultra fast time, but once you zoom in, the pulse can be as wide as you like, making it easy to measure and qualify that pulse. You actually divide that pulse by 56 to find the tick time, and the tick time generally is 3 microseconds. There are others, but in most cases, those that I've seen, I don't know about yourself, it's always been 3 microseconds. Now the time interval of subsequent falling edges, Nibbles defines the bit value. So what do we mean by that? Single edge nibble transmission. We only measure from a falling edge to a falling edge. We measure the time and we utilize the time and the tick time to define what actually bit value is in that pulse. So what are the characteristics of scent? Given scent utilises a point-to-point topology, a vehicle may utilise any number of scent sensors. I don't know whether there is a limit.
It's not listed in the protocol as far as I know.
No, I think given it's point-to-point, it's the same as having perhaps the same number of sensors you've had traditionally that have been analogue. Why not digitise them? The time interval, as we said, between falling edges in a packet can represent a maximum of 16 different values, so 0 to 15 is a nibble value. Scent transmits both fast and slow data simultaneously. Now that might be a bit confusing at the moment, but as we move on you'll see that scent is very clever in that it sends critical information required at a higher speed over sent fast, but it then can send additional data, less important, via sent slow. Jumping the gun, there you are. Sent fast contains the critical values, things like fuel pressure, so basically what it was designed to measure. Sent slow data contains less critical things, data such as error codes and information about the sensor, and that's delivered in pieces over multiple packets, so 16 to 18 fast packets, which are then reassembled by the ECU to form that piece of data, the slow, less critical data. Given a sense sensor utilises a point-to-point topology, it would not be directly linked to a gateway. So you wouldn't link from, let's say, the DPF pressure sensor to a gateway, or that would not be the gateway itself. However, the receiving ECU to which the DPF pressure sensor reports could well be a gateway, and then could share the information from the sense sensor onto other networks. It incorporates error detection and validates each packet of data, which is then verified by the receiving ECU. So we haven't had that before. Traditionally, we've been able to sense an open circuit or a short circuit, but this is now qualifying each and every packet of data that goes to the ECU, that this is what I'm sending, is it correct? And the ECU can verify that. Sent transmissions are not polarity conscious, as the data remains the same when the signal is inverted. Now, I haven't seen this, but if it is just edge to edge, whether the polarity is positive or negative, the edges would remain in the same position. So in which case, it seems to be fault tolerant from an inversion aspect. The maximum payload of a sent packet is 24 bits, which can be split depending on the sensor type. So it's not unusual, and we have an example of this, to have 2 times 12-bit sensors, or maybe 1 times 16-bit sensor, high resolution, and 1 8-bit sensor, all in one unit. It's up to the manufacturer what they decide to do with a particular sensor. So what does a sent packet look like? Here it is, again decoded by PicoScope, and I've broken it down into the various segments. 4 segments form the main fields of a single sent packet. So the first one is the all-important calibration pulse. You must measure that correctly, divide the measured value by 56 and find the tick time. Status and communication nibble, so everything now after the calibration pulse is a nibble. That contains information about the sensor mode, mode of operation, and partial message segments transmitted over several packets. So it's giving the heads up really as to what's contained, what's to follow within the field, data field. Now the data, of course, the data nibble has exactly that. It contains the measured parameter data. So whatever it was predominantly designed to deliver, so mass airflow, temperature, pressure. And finally the checksum. There it is again, a 4-bit code generated by the sensor to validate each packet of data, which is then verified by the receiving ECU. So checksum, it's common to these protocols that we've discussed through this series of videos. One form or another, there is a way of validating the packet sent and the packet received. And here we are above on the right hand side, point 1, we're measuring the calibration, the calibration pulse. Notice where we're measuring from, edge to edge. That's falling edge, not rising edge. Falling edge is much crisper than a rising edge. Edge to edge, and the same for every subsequent pulse.
So to summarise, Steve, if we're looking at this data from a diagnostic point of view, what we can see in here additionally to just ones and zeros effectively is the key things to look out for is the calibration pulse, which we can then divide by 56 to get the tick time, which is only important really when we come to decoding, just to make sure we're using the right decoder, because there are some options within the software for various different types of sensor. And then Knowing what type of sensor it is also important for the decoder. But when we do the videos on this, we'll be able to see the sort of information that you can see within the decoder isn't the same as with the other protocols. This is different.
Yes.
Because we get typically 2 sets of data in the fast and 1 set of data in the slow, as well as information about the sensor, error messages, and the all-important checksum.
Yes.
So there's lots in here. So although the actual measured signal isn't that interesting, I would say the diagnostic gold in terms of sense sensors comes from the decoder.
Yeah.
And therefore knowing how to access the information we need to use the decoder is the critical thing.
Yes. Yeah.
So if we use our can messages be sent, our messages is being sent, and the node, it's the R messages being sent is the critical measurement was sent, I would say.
Yeah. On that note, within the decoder table, when we decode on the fast sent, we get a lot of data immediately, not what I'd class as decoded, but decimal values that we recognize that increase and decrease with whatever's being measured. So whilst we're not converting it into human readable, let me rephrase that, the correct units. So we're not getting numbers in the correct units, say for example degrees centigrade. What we do get is, as the temperature increases, a decimal value that rises and a decimal value that falls. It's not precise diagnosis, but you're qualifying that the sensor's doing something and outputting something as well.
Yeah, so as you squeeze, bang or rub that particular sensor, you get the relevant change in the decimal
get the change, yeah.
Data.
Force a change and see if it's working. Yeah.
It's a quick and dirty method.
It works. We'll take what we can get in diagnosis sometimes. So scent tips, here we go. The scent protocol will interpret a voltage of 4.1 and above as a high level. Again, here we are, little bits that may be helpful during diagnosis. It tolerates something other than, we're not saying you've got to be at 5 volts, 4.1 and above. Equally, at the opposite end, interpret a voltage of 0.5 and below. While scent utilises a tick time of 3 microseconds, this can increase to 90 microseconds, which is why measuring that calibration pulse means you can apply the right conversion to your data. PicoScope decodes both scent fast and scent slow messages. I've put a note there, use 200 millisecond divisions. You do need a reasonable sample rate. It's all covered in our guided test, but 200 milliseconds, that gives you 2 seconds of data across the screen. So you get plenty of data and enough time for the slow messages to come through so you don't miss anything. Depending on the scent version and the sensor type, information on how to scale and offset the sensor output can be found in the scent slow decoder. So here we are really drilling down to true decoding into human readable values, because not all sensors, but a lot of sense sensors give you information in the decoder table on how to convert the raw values into true values, including the units as well. A single 2 times 12-bit sense sensor, for example 2 pressure sensors in 1 unit, will divide the 6 nibble data field equally. So here's 2 12-bit sensors with 6 nibble output. The first 3 nibbles representing sensor 1 and the second 3 nibbles sensor 2. So that could be, if we take a differential pressure sensor, we want the pressure before and the pressure after. So we'll utilise 3 nibbles for before, 3 nibbles for after. Channel 1 and channel 2 of the PicoScope scent fast decoder are always displayed in decimal values and correlate to the raw sensor output. So that's a little bit of gold there, is what you're always getting in those channels is decimal values. Admittedly, they've got to be scaled and offset, but as you said there, if we activate the sensor, apply pressure, apply temperature, and we see a change in those values, there is an output from the sensor. Powering a scent sensor from sleep results in an output of just 5 volts for approximately 38 milliseconds. So we found this certainly on the sensor that we are testing, and it's repeated every single time. So before transmission starts, because simply powering one of these sensors on the bench, you will start to get sent data from there. But there's always this window, whether it's a calibration, whether it's a wake up for itself, I'm not sure, but it's repeated time and time again. So it would be good to compare that with other scent sensors. And the chart below converts the nibble time with a tick time of 3 microseconds to hex, binary and decimal. So if we take the first column, for example, if we measured a nibble time of 36 microseconds, the number of ticks, which is the nibble time divided by 3, well, that's 12. 12 in the conversion chart equates to a hexadecimal 0, a binary 0 or a decimal 0. So we'll keep this chart available. It will be included on the forum, so you'll be able to apply a conversion to the data you've acquired, assuming you've got a tick time of 3 microseconds. Okay, so on that we're going to go into the workshop now and carry out some testing of a scent sensor. This will be at a bench, and run through how we actually use those values and convert them into human readable. Some of the features of scent output, and then also look at what's tucked away in the scent slow decoder as well. All right, thank you for watching. Welcome to this video on scent, the single edge nibble transmission. Now we are approaching this from a slightly different angle this time, because where we've used the CAN process for diagnosis. We're happy with all that. What we want to show you here is anybody could do this. This is just simply powering up a scent sensor on the bench and then applying a physical value to it. You said, Andy, was it if you scratch it, sniff it, squeeze it?
Squeeze, bang, rub.
Yeah, that's it, add temperature. We'll force a change of state from this sensor. So if we just describe the setup, we've got Mitivac connected to a DPF pressure sensor. So this is Denso device. We are going to apply positive and negative pressure. In fact, it doesn't matter which one, we'll go with positive. We'll use the WPS pressure transducer as well. So what we'll do is, in fact, if we switch that on, let that power go through each range 1, 2 and 3, because it's got to calibrate. We'll put this in line with the Mitivac and we'll apply pressure to this sensor. We're using a benchtop power supply to supply it with 5 volts. In effect, we're going to get data from it, because as soon as you power a scent sensor on the bench, it will start spitting out data immediately. And we'll use we've got 2 decoders for scent, one for scent slow, that's got data about the sensor, sort of less critical data like temperature. And then scent fast, which has got all the pressure values in. So whatever we do pressure-wise, what we apply to the sensor, we get an immediate response on the scent fast. So all being well, we should be able to get that to range 2. Yeah, can you connect that, Andy? So we go here. So what we wanted to capture first of all was the powering up of the scent sensor, because we've seen a pattern here whereby you go from power up, and then there's what I'll get a pulse, if you like, an interval of about, I think it was about 38 milliseconds. So there could be diagnostic value in that. So Andy, could you just power that up, please? There we go. So if we zoom in here, we'll see that the scent sensor is starting to pour out data. But as the power went on, we got up to they're both on the same range, but I will use the red. The red is the power supply. At this point here, which was 4.36 volt, the scent sensor became active. Now the pulse, or the pause, if you like, is from those 2 points there. I would say 38 milli. That wasn't a bad guess, was it? It's like we've done it before.
Maybe.
Okay, so just something that we wanted to share in case that can be of diagnostic value. We're seeing it repeated every time, so it's almost like it's a configuration within the sensor itself. What we want to do now is convert the data coming from the sensor into human readable values, because we're just getting raw data coming back. These are data bytes. How will we do that? We'll go to guided tests, of course. So open our guided test. It's a communication network and it is sent. We'll start with sent slow. Open the guidance settings file. Behind the scenes you'll notice there that it's loading in the waveform, but here's our configuration. It's showing a pressure and temperature sensor here. It's kind of exactly what we've got on the bench. We're obviously not connected to a vehicle. We've got our own power supply going in and we're tapping into the signal wiring. There is an example waveform and the decoder is already active. This is the important bit. There is so much information in here about how scent works. So this further guidance, Andy, you said just-in-time training.
Yeah, just-in-time learning. It's vital that if you have, this is a great resource. So if you're spending a bit of time researching how these things work, this is one, you've got the test and measurement capability as well as the learning resource all in one place, ready to go.
Yeah. I often think about back at college days when you had to try and source information from books and that. Now it's just out there, isn't it? And the guided test, everyone is accessible without a PicoScope connected, so you've got access to technical information for free.
Yeah.
Okay, so let's just have a look what we've got here. We've got the sent signal, and I guess we should take a reference of this because we wanted to know, are we on the right wire?
Well, not just that. Is it actually sent, or are you connected to some other switching voltage?
I guess so. Yeah. I mean,
because could it? How do you identify whether it's sent? Is it LIN?
Yeah.
Obviously, it just looks like an intelligent sensor.
Yeah.
Or it looks like, probably more realistically, it looks like any other analog sensor.
Which is why we have that, because that was the misinterpretation of this.
Yeah. So I think being able to identify it as a sense sensor is the first step.
Yeah.
And that pulse at the beginning is one of those things that you can do to identify it. It's also important to talk about the voltage levels.
Yes.
How it distinguishes itself from LIN.
Yeah.
And how would it distinguish itself from a PWM type input or a frequency
the one
sensor?
Sorry to interrupt you. The one that springs to mind for me is mass airflow, where just a frequency output in relation to airflow. That would just purely be a change in frequency. This has got far much more in there. So we powered up. The dark blue waveform is our sent data. The pale blue is our reference waveform, 0 to 5 volt, and I think I would accept that as being sent.
Yeah.
Yeah. We just get the reference. If we're comparing the two, I think we've got the right sensor, and we're definitely capturing the right protocol. Right. What we wanted to share here was the fact that in here we have this slow data. It might be temperature, it might be diagnostic information about the sensor itself. This is information that is not required to be sent at high speed. We don't need high resolution for this data, unlike we would to know if we were looking at the DPF pressure. We want to be informed of that rapidly. We want ultimate resolution. What's intriguing in here is this section here. Now, Andy, I know you've done some work with this, haven't you, with SET? Yeah. And this is looking at the supplementary channel. So in here we've got pressure on channels 1 and 2. It's a DPF pressure sensor. So there's 2 pressure sensors in one, both of which are 12-bit resolution. But there's also a supplementary channel which gives temperature, and that is hidden in the slow decoder. So as we scroll down, information here tells us that there is temperature available in a supplementary channel. And when we look at supplementary channel data, we see there that we have raw data here, 0208OC, those are hex values. And Pico has already decoded the data, that conversion from 0208OC into decimal 700. 700. How do we get that into something that we recognise, degrees centigrade? Well, there is a formula that comes with that. Let's try and make life a little bit easy. So let's add a filter. And let's go to something like 8-bit message ID. We want within there contains, and we'll put in the search criteria, supplementary. Have I spelled that correctly? Supplementary data channel, and that is #1. So there we have now, out of all that data, just the data that we're interested in. We've taken away information about the sensor, these kind of things, and we're interested in the data value here. We can see there that it looks as though we have momentarily 700 and 699. Something changed. The temperature in here is fixed, so we're not really going to see much of a change. But what we'll do, we'll export this data and we'll put this into our LIN folder. Let's put it into LIN Studies. This is from a Mercedes Sprinter, and we'll call this Test 1 Export Sense Slow, and save that. Now,
so what you've done there, Steve, is you've filtered all of the data that's available to us, which is all the data on the slow channel, down to just the supplementary data, which we happen to know for this sensor because it actually tells us in the slow data that is a temperature value.
Yeah.
However, it's 700. Are you sunburned? So it's obviously
that's pretty warm, isn't it? If it's degrees C. Yeah.
So it's obviously not in degrees C.
Yeah.
So the next step, what we need to do, we need to, as you said, translate that, for want of a better word, into something human readable.
Yes.
So we know that's temperature data.
Yeah.
We know that it came over in hex. The decoder has changed it into decimal as well, so we have it in both values. And we've now taken that data, just the temperature data, the supplementary data on channel 1, and placed it in an Excel file.
Yeah. Which then takes us onto our Excel skills.
Yes.
Which are
beyond the scope of this video.
Yeah.
However,
but let's do it, shall we? Let's see if we can limp through Excel. I know that you've been a champion of it because the stuff we've done with OBD, with mass airflow and calculating it. There's so much value in Excel. There's so many things that you can do for converting data. We'll go to Mercedes Study. What I'm going to do is open, although it was saved as a .csv file, we're going to open it with Excel, only because we want to take advantage of all the features within there. This is the column we're interested in. So I'm just going to copy that column, so that's right click, place it over here. I just don't want to disrupt any raw data. Now then, we need to add a formula to this, so we'll call this temperature conversion. Now then, if I'm going from memory, our temperature value is the raw data, so if I put in equals, so that would be L2, and I think it was open brackets. Can you remember this from memory? L2 divided by 8. Yes. I knew
minus 73.
And why is that, Andy?
Okay, so in the protocols, which you'll be able to get at, we're going to provide some information around this.
Yeah, it's all.
And we're also going to provide where we got these formulas for. Basically, in the scent protocol, certain measurements, such as temperature, are always the same no matter what the sensor is part of the protocol. And it's got quite a high resolution for measuring temperature. So it's in steps of 0.25 degrees. And that's basically a conversion from decimal into degrees C's, just using the formula. All I've done is transpose the formula that we'll provide. We will provide it, yeah. And that there, it gives you it in degrees C. Yeah. So just a tip for Excel. There was the formula. So it was the raw data value, which is 699 in this case. That's converted from the raw data in hex. PicoScope has already done that for you. Divided by 8 minus 73 because that's the offset for degrees centigrade. Now if I just double click here in this corner,
you see there that it automatically now does the calculation for every single segment of data. So in fact, we should have done, like you said, Andy, if we'd warmed that up this morning, we'd have seen that temperature rise, we'd have been able to graph that. But nevertheless, I think it's about right in here this morning, isn't it, that temperature, how it feels. 14 degrees, 14, with occasionally 14 and a half. So
middle of summer in Port Talbot. So and that gives us a very approximate reading. So if you wanted to validate a sensor that's fitted for something like a temperature reading, this is a method you can use to take data that looks almost just some lines and turn it into a reading in degrees C. The reason for the minus 73 at the end is the raw data divided by 8 is in Kelvin. And we need to convert the Kelvin into degrees C.
Gotcha.
If you wanted it in degrees Fahrenheit, you would just use a different conversion factor from Kelvin.
Yeah. So in fact, thanks for that, because when we put it up on the forum, we'll make sure you've got both.
Okay, yeah.
And for anybody who wants it in Kelvin, we'll put it in Kelvin as well.
Okay, the only people you reading that in Kelvin are the people on the Starship Enterprise.
Right.
But they can read it in hex anyway.
Okay, they can read straight from hex. Just a quick one that you might find useful. If I right-click on this column, and I think it's insert, is it a line graph? Yeah, we get a little chart there for the temperature. Now that at first glance looks like the temperature's going up and down. You've got to look at the scaling. The scaling, it's going up from 14.38 to 14.5. I'm glad it's done that, because normally a temperature graph to look at is a straight line. It's really boring. So.
But yeah, and I think it's just worth noting, we can take this to the 0.25 resolution if we wanted to.
Yeah.
We've just rounded it up to 73.
Okay, good stuff. All right, so that's sense slow. Now think about that for a second. All that data was for free. That is just being churned out. We've been able to grab the data and convert it. Let's have a look now at how we're going to look at the sent fast data, because that's a different ball game. So
I think it's important to say now, or to reiterate maybe, is there is one wire come out of this sensor.
Yes.
On that single wire, so far we have got temperature data.
Yes.
There are other data we haven't done anything with. They normally, not on this, unfortunately, this is, as you'll see in a second, why we're doing this procedure the way we'll be doing it in a second, is normally within the sent slow data is information about the sent fast channels. And basically a way of converting them, the information required, a min and max value, X and Y values for that sensor are contained within the sent slow data. So also error codes are sent out on the sent slow channel. One wire, so far we've only really taken temperature from it, but there is a number of other data streams being sent on that. And these are data that are trending over time. They're not rapidly changing, therefore they're on the slow channel. Mm-hmm. We're now going to look at the fast channel, which is normally the two primary measurements of the device. So if this was an air mass meter, you would have temperature on slow and air mass on the fast channel.
Yeah. No, thank you for that. You're absolutely right that what we're going to do now is, it's not so much a cheat, but we're going to use a different formula for trying to calculate the output. A lot of sense sensors do give us coordinates, X and Y, and you would find them in sense slow. We haven't got them. This one is unidentified, unfortunately, and you do get that occasionally. There'll be sensors that are not covered fully in the sense slow. Nevertheless, we can use another option. Okay, so for that one then, we're going to, well, no, what I will do, before I do any more, let's get this up to the waveform library.
Yeah.
So we know that this has come from a
Sprinter.
Mercedes Sprinter, yeah, thank you. So Mercedes Sprinter, this is already populated. We'll use the current waveform. We'll keep that as is. It's sent bus. Yeah. We're happy to save and upload. The software will let us. Had we not filled in this area fully, we wouldn't be able to click here, save and upload. I'm hoping that's going to go. Yeah. So you'll be able to pull down this waveform and do exactly the same. Operate the sent slow decoder, maybe export, have a play with Excel. And the same with sent fast, which is what we're going to do now. All right, so let's go guided tests. Let's come back out and we'll now go to Sent Fast, Guide and Settings file. Once again, same connection chart, but more information, further guidance on Sent Fast. We'll close that down. Actually, this is probably worth mentioning. We mentioned this in the video, didn't we, about how we have various packets. So do you want to carry on with that one, Andy?
Yeah, so for every 18 packets, or it's between 16 and 18.
16 and 18, depending on whether it's an enhanced message or not.
Exactly. Yeah. Between 16 and 18 fast packets will contain one slow send packet. So we could use the send packet that's 18. You've just put the cursors on. And it's 18?
It is. It's 18. I've just counted them.
Okay.
So yeah, 18 fast packets of data, and we've got one slow message, and there it is. Yeah, and the slow message is in hex. It's 000009. So quite a cute protocol how it does that, isn't it? It's almost like
it's quite clever how the amount of wiring they reduced, the number of sensors they've reduced, and just by packaging the data in this way.
Yeah, and look what we're getting on that single wire.
Yeah.
Yeah. All right, so that is the example waveform. Let's get raw data by just pressing the start button and getting data from our sensor. What we don't want to do is decode the example waveform.
No.
Because that's not relevant to us at all. Okay, so we're collecting data. Before we actually move on, let's have a look at, we talked about the calibration pulse, didn't we, in the video for Scent. And if I zoom in here, that calibration pulse is the first pulse. In fact, the decoder's done it for it. We measure from falling edge to falling edge. That is single edge nibble transmission. So we only measure falling edge. And here we are 167.8. And if we get the calculator up, and we'll go to standard, and let's say it was 168 microseconds divided by 56 to find the tick time, 3 microseconds. Yeah, because that is important. We don't have to worry about it too much because Pico's done the work already, but if you wanted to drill down to try to identify what a data byte refers to, you would need to know the tick time.
Yeah, and it's important, if you have problems decoding sent messages, one of the options you have in the decoder is tick time. And so you might have a sensor that's operating on a slightly different tick time. In the decoder, you can change that if you want to show them where.
Yeah, well, thanks for that, because 3 microsecond tick time is pretty generic. You do find that. With that said, you can amend that. So you click on the decoder and you would change it here, tick time, depending on what you wanted. Also, depending on the sensor that you're using, we know we've got a 12-bit or 2 12-bit sensors inside this sensor. We can select it from here.
But there are other options for different types of sensors.
Yeah, there they are.
And that's where you can select it. So you do need, and I always say it, and I expect what you inspect. You do need to know what you're doing. You do need to know what type of sensor you're measuring.
Yes.
Because in the decoder, you need to add that. You can make those changes if you need to. I've looked at quite a few of these now, and I have never seen anything other than 3 as a tick time.
Yes.
So it seems to be fairly standard.
I'm glad you said that, because you could have been presented here with numerous errors and blame your measurement technique, blame your configuration, blame your setup till you're proved otherwise. So whilst the guided test helps you out, gets you off and running, you will need to make amendments for the type of sensor that you're working on. All right, so we're going to focus purely on, let me close the zoom. We are going to focus on channel 1 and channel 2, because we are going to apply pressure to this sensor now, and we're going to see that channel 1 and channel 2 will change. We want to also capture that pressure. So on channel C, we have a pressure transducer. So I click on probes, WPS 500, range 2. And we want that on, I think it's plus or minus 1.4 bar. And run PicoScope. I'm going to remove some of the decoders because it's getting quite cluttered now. So we'll take away the slow decoder, sense slow, we'll delete. Yeah. Just give that a moment to catch up. And let's close the rulers. And we'll pull up the table. I really want you to focus on, I think it's channel 1 at the moment. So, Andy, if you could just apply, oh actually, sorry, I don't have channel C active there. There we are. In fact, let me if I, let me drag the decoder in the table view out of the way. Yeah, so if you apply some pressure, there we go. So we see a change of state there. Let's just stop the scope and go back. Go back one more. So there was clearly a change of state, wasn't there, in pressure? So the green waveform is pressure. Let's just pull a ruler down. So at that point, our pressure was 250 millibar. Here we were at 500 millibar. If we amend the decoder and we ask the decoder to decode between the time rulers, click on, click finish. Now nothing's going to happen because we don't have time rulers in place, but I want to focus on the area where we went from one state to another, where there was change. So you can see in the graph view there, the adornment, that we are only decoding between the time rulers. So we've minimized the data that we've got to look at. And if we start slowly here, we were at channel 1 was 119. Then as we scroll down, you'll see we change from 119. So now our raw data on channel 1 is changing in relation to the pressure that's been applied to test port 1. With that, let's have a look at the pressure at this point here. So we know we've got a ruler on. Let's add a measurement. And we'll have channel C, the mean value between the rulers. So yeah, we were fine there, weren't we? 252, 252. And let's do the same again here. $500. Shall we go with that?
I'll go with that.
252 and 500. And let's come back here. We'll go to our sent fast decoder. And we're decoding only between the time rulers. So we know, and let's make a note of this. 252 millibar. Is equal to an output from the sensor at this point in time of 1120. That's a 12-bit encoded value. 1120. And then the other one was 500 millibar, wasn't it?
Yeah.
As good as. And our output at 500 millibar check the measurements. Yeah. The sent decoder. We'll see it there as 1955. We're only decoding just that bit there. So we know that a 12-bit encoded value of 1955 equates to 500 millibar. 1955. So what have we determined there?
Well, to begin with, what we've noticed is the sensor's reacting.
Yes.
And it's reacting in a way that we'd imagine it would. The value has gone from a low value to a higher value with an increase in pressure.
Yes.
So that could be enough.
Yeah.
We know the sensor's reacting. Is it reacting correctly?
Good point. I mean, what we could do, there's nothing to stop us just simply exporting this data to Excel and graphing column 1, channel 1.
Yeah.
We'll see a change in pressure. we know that we'll get a replication of what we've got here on the scope, but what we'd like to do is convert that into human readable value to basically decode. So with that, we'll use the export feature of just...
So you want to export a bit more data than that?
Yes, thank you, because we want to graph, so we graph the change. Thank you, Andy. So what I was about to do was only export between the time rulers where there was no change in pressure. What we're doing now is we're exporting data from a low pressure to a high pressure. So we'll get all of this. Export that all. So this is test 2, and this is sent fast. Right click, we'll open with Excel. And this is the column of interest. I could, if I wanted to, just click here, insert, line. Does that look familiar?
Yeah.
Yeah, that's exactly what we've done, isn't it? All we've done, we've just exported the data on channel 1, and it's in a coded value.
I think it's important to stress here, Steve, that is at this point, if you were going across the measuring range of the sensor and you graphed it out like that, just by doing that simple, if you had dropouts, spikes down or up in the data value, you could probably deduce that this sensor is probably giving you erroneous data.
Yeah.
The fact that it's replicated what the measured value of the WPS or the shape of that probably suggests that it's doing okay.
Yeah. And certainly for dropout, the better choice would be the scope. Yeah. With that said,
but you don't know, because if it's dropping out within allowable ranges, you might not get a code.
Okay.
But you might get erroneous readings or misbehaving vehicles. And because the scope is only measuring that, we need to measure that as well.
Yes.
So we need to then graph it to see if there is any dropouts measured by the sensor.
Yes. Yeah. So we've got exactly that then, haven't we? We've got the replication, and let's just go back to Excel. There we are. So it looks as good as it gets, really, isn't it?
It's pretty good.
We need to go one step further, though, now, because...
We'd like to.
Yeah.
We don't know. I don't know how many people need to, Steve. It's only people like me and you that need to go further.
Yeah, if I'm waffling, stop me. Yeah. Let's click on channel D. And like we did with Sense Slow, we'll copy that. Yeah. Paste. And we want to do some editing of this. So this is channel 1, and we'll call it copy of the data. And we'll try and convert that now into pressure values. And what we're going to do is we're going to use an Excel sheet that we've got that carries a formula that enables you to use 2 data points and uses a linear equation, actually. So with 2 data points of a physical value, which is the pressure from the pressure transducer, and 2 encoded values, we can then convert that, because we know the slope, we know actually the gradient, and how to graph this in a human readable value. So we want to go to a conversion chart that we've got, and I will post this on the forum, so we'll have this as well. Okay, so we've got this spreadsheet that has a calculation, and for us, I will actually put on the forum the 2 methods of doing this, so you'll actually have the formula. Nevertheless, we can let the spreadsheet here do the work for us. And I have to thank Ollie Hayward for his work here. Thank you so much, because this has been used time and time again. We use the values that we got. So if I use the Windows left key, we can actually get these up. So first of all, we want our decimal input value and decoded actual value. So here, this is the physical pressure value that we've measured. Okay, so it was 252 millibar, 252, and the encoded value is 1120. Here was the actual pressure value when we were at, this was 500 millibar, and the encoded value there was 1955. Enter. So you see there then, it's given us the scale and the offset that we can apply to those coded values that we got in channel 1 from PicoScope. So let's go back to sent fast, put them side by side. S2 multiplied by our scale, which is 0.297. We'll stick with that. Well, now we're going to have to put that into brackets. So you were saying maths class, Andy.
Yeah.
And now that is raw times scale plus the offset. So actually, no, I don't have to put that first bit in brackets. It's the next bit I have to put in brackets. So raw times scale plus a minus value 80646. Go with that. 80.646. Enter. So that's 251 millibar. And if I double click on this here, it will do the calculation for us. So now we're getting our values converted. So that was our raw data, and if I click here and ask Excel to put that into a line for us, we get the same again, only this time we've actually got it in a pressure value. So we're starting at approximately 250 millibar, going up to 500, which is exactly what we had in PicoScope. Let's go back to PicoScope. There we have it. Yeah, 252 and 500 millibar. My word, that's enough, I think. Yeah.
I think the only thing we need to add here is that's the way to do it when you haven't got the values. There is another way which we'll explain, but we can't do for this sensor because we don't have the values.
Yeah. What we've actually done here, we've just taken raw physical, the actual physical value that we know and the raw data, and used a linear equation to graph them and convert them, and that applies for anything, any sensor that is linear in that nature. So before we do any more, we'll get this up on the waveform library so you can have a play, you can follow along. I'll just put a note here that this is physical value applied by pump.
And it's good?
Yeah. And it's letting us save, so we click that. That's gone up to the waveform library. Yeah, there's the confirmation. Perfect. All right, so there we have it. It's all bench testing. It's a way of converting raw values, 12-bit encoded values, into true values, human readable values.
Yeah, basically what we've done there, Steve, is we've applied our network diagnostic process, our CAN process. Mm-hmm. We haven't checked if messages can be sent because it's a simple 3-wire device. I'm sure everyone watching this video is capable of that. We've gone straight to our messages being sent. Yes, but we've gone a little bit further with those messages, and we've been able to determine whether those messages, well, not only are they being sent, but are they being sent, and are they realistic values, and do they reflect actual measurements that we can take externally, much like you would do to verify any DPF pressure sensor. We've done something very, very similar, but we've done the extra step of decoding the data into human readable.
Right. Thank you for watching.